states of matter. And I think that a lot of this today is really like common sense, people. Common sense. This is a random video here. Hold on. Is this the... There you go.
You have a super yellow Pandora station.
I do have a super yellow Pandora station. Somebody renamed all my Pandora stations, and I don't know what's on each station. Okay. Okay, so watch this first. Take notes in your head. Don't write.
Sometimes, when a fish is reeled up to the surface, it will appear inflated, with its eyes bulging out of their sockets and its stomach projecting out of its mouth, as if it's been blown up like a balloon. This type of bodily damage, caused by rapid changes in pressure, is called barotrauma. Under the sea, pressure increases by 14.7 pounds per square inch for every 33-foot increase in depth. So take the yellow eye rockfish, which can live as deep as 1,800 feet, where there's over 800 pounds of pressure on every square inch. That's equivalent to the weight of a polar bear balancing on a quarter. Now, Boyle's gas law states that the volume of a gas is inversely related to pressure. So,
okay, you guys bring your box of beer with you today? You got it? I didn't tell you about. Did you bring it? You brought it, Lucas. Don't lie. Bring it. Okay. So you got your box of air. Everybody's got a box of air. Apply pressure to it. Okay. What happened to the volume of your box? It got smaller. So increasing pressure does what to volume? Makes it smaller. Okay. Every day bring that box because we're going to be using this a lot. Okay. So you should know they're indirectly related. Inversely related. Bigger pressure, smaller volume. Okay. Take your box of air back out. You put it away. Come on, people. Okay. So release the pressure. What happens to volume? It expands. So lower pressure, higher volume. If I send a balloon up into space, what's going to happen to it?
Less pressure.
Less pressure, so it gets bigger and bigger and bigger and bigger, and then the elastic can't handle it anymore, and it pops. Okay, if I put a balloon and I send it to the depths of the ocean.
No, it'll deflate until like shrinks.
It would just, what's the word for that? Compress. It would probably compress so much. It would be like that big. I don't know that it would pop, actually. It would just compress. Or maybe even turn solid. So it's going to, the air has nowhere to go, but it gets so close to each other that it gets a smaller volume. The gas particles are this far apart, then they get this far apart. Cool.
Any air-filled spaces like a rockfish's swim bladder or human lungs will compress as they descend deeper and expand as they ascend. After a fish bites a fisherman's hook and is quickly reeled up to the surface, the air in its swim bladder begins to expand. Its rapid expansion actually forces the fish's stomach out of its mouth, while the increased internal pressure pushes its eyes out of their sockets, a condition called exophthalmia. Sometimes rockfish eyes will even have a crystallized appearance from corneal emphysemas, little gas bubbles that build up inside the cornea. Thankfully, a scuba diver doesn't have a closed swim bladder to worry about. A diver can regulate pressure in her lungs by breathing out as she ascends, but must be wary of other laws of physics that are at play under the sea. Henry's law states that the amount of a gas that dissolves in a liquid is proportional to its partial pressure.
Dissolved gas in a liquid. Where would you find that in the real world? Well, it's got to be a dissolved gas. So we're talking about gas around. So carbonated beverages, soda, right? Okay. So what happens when you open up a soda? It goes, psst. What is that?
The pressure released.
What pressure being released? The pressure that was where in the bottle? At the top. Right. This pressure at the top. You can't see it, but there's a ton of carbon dioxide that's pressurizing the whole system. You keep all the bubbles in the liquid, and then at the top there's just a bunch of gases holding them down. When you open it, all that goes away, and what happens down here? They slowly start to bubble out because there's nothing forcing them to stay in the liquid anymore. So then eventually it does go flat. Wow. Yeah. So if you want to, if you would like to keep the pressure above, you have to repressurize the system every time. And I don't think anybody has a contraption like that at home. Probably. So we all have to drink flat soda.
The air a diver breathes is 78% nitrogen. At a higher pressure under the sea, the nitrogen from the air in a scuba tank diffuses into a diver's tissues in greater concentrations than it would on land. If the diver ascends too quickly, This built-up nitrogen can come out of solution and form microbubbles in her tissues, blood, and joints, causing decompression sickness, aka the bends. This is similar to the fizz of carbon dioxide coming out of your soda. Gas comes out of solution when the pressure is released, but for a diver, the bubbles cause severe pain and sometimes even death. Divers avoid falling victim to the bends by rising slowly and taking breaks along the way, called decompression stops, so the gas has time to diffuse back out of their tissues and to be released through their breath. Just as a diver needs decompression, for a fish to recover, it needs recompression, which can be accomplished by putting it back in the sea. But that doesn't mean fish should just be tossed overboard. An inflated body will float and get scooped up by a hungry sea lion or pecked at by seagulls. There's a common myth that piercing its stomach with a needle will let air escape, allowing the fish to swim back down on its own. But that is one balloon that shouldn't be popped. To return a fish properly to its habitat, fishermen can use a descending device instead, to lower it on a fishing line and release it at the right depth. As it heads home and recompression reduces gas volume, its eyes can return to their sockets and heal, and its stomach can move back into place. This fish will live to see another day, once more free to swim, eat, reproduce, and replenish the population.
Sounds kind of cool, right? So I like that video because it's interesting. But also, the conference I was at yesterday, this girl who was a National Geographic Young Explorer, she got a grant. You have to be between the ages of 18 and 25, so you're getting there. She got a grant to travel the world in a submarine. Right? So she was amazing. Like, I want to be her when I grow up, right? She is awesome. And she got the chance to basically do research underwater. And she's like one of the only women who's a pilot of a submarine. And so she got to go to the area right on the coast, so not quite the continental shelf, but kind of the continental shelf, or continental something, geology term, yeah? And then down further is the continental shelf, and that's where all the coral reefs are, and the like beautiful aquatic life, right? And then she said, once you get to the edge of the continental shelf, you look down, and it's just dark. You can't see anything. And that's where the continental shelf stops, and you fall into the real ocean, right? And so it's deep, deep, deep. What's the deepest part of the ocean? Mariana Trench, right? So that's like 100,000 feet, if I'm not approximately right. Hugely deep, right? Most submarines only go down to like 70,000 feet, something like that. Okay, so she got to go down to the Mariana, or no, she has not. There's only been, how many people have been to the Mariana Trench? Anybody? 3. Good guess. Who was one of the most recent ones? James Cameron. How am I the only person that didn't know this? Like, how do you? I don't know pop culture.
I just watched one.
There you go. TV. It's good for you for random things like this. So he went down there, and he's filmed Avatar, Alien, Titanic, stuff like that. So they actually went down there for inspiration to create new monsters, right? So I don't know what it's called in Avatar, but they have the huge plant that sucks. It's like a tube and it sucks somebody in.
Plant?
I think it was like a plant animal.
It's an alien.
It's an alien. Okay. So anyway, it's like 15 feet high. It's huge. But he actually was inspired to do that by something he saw in the Mariana Trench, which is like this big. And it's a little bitty plant that actually does suck
it's
something
not
in.
like an actual plant.
No, it was Avatar. Maybe it was an Avatar. No, it's like deep sea boat. No, so he was inspired by something he saw there. But anyway, so she was really inspirational. She started a program for getting females excited about science, so women in science and engineering, but guys can be excited about science and engineering. It's just there's a lot of guys in science and engineering, so she was trying to bump up the female population there. And so she started a program called Female Submarine Pilots and Robotics, or something like that. And so she started all these little camps across the world internationally. And you build a robot that's a submarine, and it lights up, and you can send it down to about 100 meters. And you can explore, and you can do science experiments and stuff like that on it. So anyway, she's trying to change the world, and kudos to her, because that was awesome. So I wanted to show you that and then share it, because I got the goosebumps right now, because it was amazing, to be inspired by somebody who's just I just want to explore the ocean. And then now she's doing all these really great things about educating other people on it. Because the ocean is a significant part of our world. and we know very little about it. It's like 70% of our world, right? So, and another thing she's doing, she's submitting a proposal on it tomorrow to see if she can get funding for it, is black to black. So she's going to send a 360-degree camera, cameras all the way around, down to the depths of the ocean, all the way down, and video the whole time, and light up, just so we can see everything. And they're going to take that, they're going to send it back up the ocean, levels, and then take it, hook it up to a weather balloon, and make it straight up to outer space. So black to black, black of the ocean, black of outer space. That's cool. And then once it gets up too high, what's going to happen to the balloon? It's going to expand and pop. And then she said, it's going to fall at terminal velocity all the way back down to Earth. And then, cross your fingers, a parachute will go off and catch it before it hits the ground, because they want the video. So she said, we're banking on this parachute to time right and come out whenever it needs to, so that the camera survives. But kind of cool. So do something with your lives, people. That was the goal of that. Do something with your lives that helps the world. Got it? That is my task to you. I feel like I got more to do. Okay, so let's talk about that chemistry. Phases of matter. Who knows the 4 states of matter? Solid, liquid, plasma. What is plasma?
Very energetic.
Very energetic.
Higher than gas?
Gas particles, right.
Yeah.
It's ionized gas particles. And where would we see that in the world?
Lightning.
Kind of lightning, yeah, that's one kind of form of it. Aurora borealis, the lights of the Arctic, right? That's why there's different colors, because there's different gas particles that are excited, different elements. And that's like halfway what outer space is made of. Yeah.
It's for like grapes in the microwave.
Yep. Have you seen that YouTube video?
What?
I cannot. I've done it. Okay, you're gonna have to do that on your own time, because there's words in there that I cannot put up on the board. I've done it once, and I was like, oh my gosh, I'm gonna get fired. But I didn't get fired, obviously, because I'm your teacher. On your own time. Great plasma. Look it up. Not right now. Nope, it's displayed. Tried that too. Okay, so anyway, we're not really going to talk about plasma that much, because we're more in chemistry than physics, and that's more of a physics deal. Yes, I'm just going to explain a little bit first, and then you can write here. Okay? What's up? So, solid to liquid to gas. We know the phases of the phase changes. Tell me thumbs up. You know melting. You know vaporization or evaporation. And you know backwards. You know condensation. And guess what? You know freezing, right? None of that's new. But which of these 3 states of matter is the highest kinetic energy, or has the highest kinetic energy, meaning the highest amount of motion? Gas, right? Okay. So this stuff over here has high kinetic energy. Ke, kinetic energy. This stuff over here has low kinetic energy. All right? How do I get something from low kinetic energy to high kinetic energy? What do you think I need to do to it? Okay, we'll give it energy that would make them become a bit more motionful. Okay, so as you add energy, what kind of process is that based off what we learned about Tuesday? Adding energy. Endothermic. Good. So going from low energy states to high energy states, you told me that was adding energy, and adding energy is an endothermic process. And so I say process to distinguish between process and reaction, because a reaction is like 2 reactants go together, they make so many products, right? This is not a reaction. This is a physical process of phase change. So that's why I say process, just to distinguish between the 2. So vice versa, gas to solid, high energy to low energy, what kind of process would that be? Exothermic, yes, exothermic process. Okay. Because the energy has to exit it in some way or form to take that high energy crazy state down to a low kinetic energy state. So energy has to exit the system. What's that thing you do when you run and the stuff comes out of your body? Sweat. Yeah, right? And then what happens when you sweat? It evaporates. Okay, thank you. Like, my third year is like, what? I don't know what happens. What happens? No. So it evaporates, right? So liquid sweat goes to gaseous sweat, right? And that process, is that a process that's endothermic or exothermic? Okay. Because it's becoming a gas, it's going from liquid state, which is low kinetic energy, to gas, which is high kinetic energy. But it's endothermic, which means it requires energy, right? Where is it getting that energy from? Your body heat, your hot body, right? So you got to figure out how to get rid of the heat, because if your body gets too hot, enzymes denature, enzymes don't work on chemical reactions, no chemical reactions are happening, and you die, right? So it is a evolutionary process that our bodies have evolved to have to cool us down. So you should know that sweating is an endothermic process because it's taking heat from your body and it cools you down and kind of as a result. It's a good thing. Right, it's a good thing. So that's one example that some people, it's a real life example I want to make sure you're aware of. All right, so that's the states of matter. We need to talk about the molecular part of it, and then we'll talk about how they change phase a little bit more. This stuff you already started copying, yes? Okay, so I'm going to fill out this part over here as we go through. Solids, you know, they take the shape of their container. Oh, no, I have a video for this. Hold on. That demo, I have to do tomorrow because I'm not ready for it today. Okay, this guy is amazing. You will sing with me. Okay? You know this song. You don't know this song, guys? No. Come on, you gotta get out more. You know the song?
It starts with solids. I do know why. Can't change it no matter how you try. Get to the shape and all you decide with particles of precision. Liquid the fluid thing. Punch the slide fine as the pendulum swings. Watch the minute glass, always taking a shape, finding it stays the same. Gaseous, unreal, moving particles. Watch them move out and into and from. Trying the whole chain, but can't do it, no. Volume can change. Then, black on the what's it on matter? I'm shaking no oil. Like a heart, marking out a sea, like a law, making like electricity. I'm in the same gases, solid plasma. Melting, solid to liquid, absorbing energy out of endothermic chain. Increasing is the way energy removed from liquid to solid. Vaporization, liquids and gas happens in emulate. Second one is always evaporation. Remembering all boiling points, change atmospheric pressure, condensation. Ships are the way they were before. Changing gas and liquid atoms together more. Energy is removed, so in motion down exothermic chain. Changing sound with gas molecules, transmit power. Levels when apart. How it's meant to be. Energy spreading like a clean endothermic chain.
Okay. So I'm feeling it. I know you were singing with me. It's a little screamy at times, but yeah, it's good. But look at all that content knowledge, right? You know all that stuff.
Everybody would
And I'll dance. Okay, so. So let's talk about how the pressure changes the states of matter, right? And you're going to use your common sense. That's why I'm not telling you a whole lot first. We know solids are tightly packed. Did you bring your common sense with you today? Please.
It's at home with the box.
Okay, solids are tightly packed, right? Very little space in between them. If you increase the pressure on a solid, what happens to volume? Did you see that get smaller? No. Like solids, the particles are so close together, there's not really a whole lot they can do. You can't really compress them anymore. They're close. So that whenever you increase the pressure, what happens to volume? No change. No change on volume. Just because there's not a whole lot you can do. They're already fairly close together. But particles are always moving. So if you guys know every single particle in your body is vibrating right now. Yeah? So if my vibrating particles were cool enough, I could pass right straight through you because you're not actually, you're a solid, but you're like a moving solid. So if our particles our particles are repelling each other right now, that's why I can't pass through her hand. If my hand, I'm so warm, I'm so cold. So that's why we can't pass through objects because our particles repel each other. If they didn't, we could just go straight through people and things. And then we fall through the floor, though. There's some bad things that come with this, right? Okay, so we know this stuff. If I increase the thermal energy, aka the temperature of this thing, what eventually, maybe not this thing, think of an engine. Okay, there's like bolts and nuts and stuff on the engine. If the engine's really, really hot, the metal itself actually expands a little bit. It's called thermal expansion. So I just told you the answer to that one. Sorry. But increasing the temperature will cause thermal expansion. And that just means it's just a hair bigger than what it was before. It's not very much, but that's why you can't really work on engines and stuff when they're warm. You shouldn't, because you probably won't be able to get them into their appropriate places because these things have expanded. Same deal with liquid. If I have liquid, this liquid here, and I press it, and I compress it, does it really compress that much? No, the particles are like this. Is there a significant change between those? No, there's a little bit more space like between the particles, but not very much. So increasing pressure, no change in terms of the volume. Increasing the temperature, what do you think? Possibly. If you increase the temperature a little bit, not to the point where it's going to start boiling. Not where it's changing phase, but just a little bit. Maybe this again, if solids can thermally expand, liquids can probably thermally expand a little bit, but it's not significant. So I'm just going to say ditto, thermal expansion. All right, so you can see these are pretty boring. We know that liquids can flow around each other. They take the shape of their container. That's kind of old news, like Unit 1 news. So here's the new stuff, gases. Gases are cool, and that's why we have a whole chapter on gases, just gases. So what happens when you increase the pressure on your gas, your box of air? It gets significantly smaller, right? So we're like, oh yeah, totally inversely related. Increasing pressure decreases the volume of that gas. Okay, so tell me what you think happens whenever I increase the temperature on a gas. What do the particles do? They go faster and they get further apart?
Yeah.
So they spread out, so what happens to the volume? Increases the volumes, probably pretty significantly. And that's why sometimes we hit to heat things up, they expand, so you can literally see the volume expanding. All right, so this is kind of some new information, but like we already know they're loosely held, we know they're far apart, and we know that they're constantly moving. Okay, so I think you kind of pieced the picture together, but you should realize that solids have very, very, really strong attractive forces between them, which makes them stick. Liquids have somewhat strong attractive forces, which make them kind of stick. What about gases? Probably like negligible, very, very, very little attractive forces holding them together. That's why they get to go have parties out on their own, right? That's why they're so far apart. All right, so that's kind of what the summary of this all is. All right, so let's look at a graph. Oh, almost. We're almost ready for a graph. The graphs, tell me, have you ever seen one of these? No. No? Yeah? Okay, have you ever seen one before today? Or yesterday?
Oh yeah, sorry.
Okay. All right, then I need to make sure I talk about this before. I'm not sure what all they teach in previous grades, so I have to ask you. This stuff is phases of changes of state, phases of matter that are changing state. It's a lot of stuff we already talked about, though. So write down what you need to. I want to explain some of the background, okay? FYI, now you know that if I change the pressure or the temperature of this substance, I can actually force it to become any other phase of matter. I can make it go to solid if I want to. Like we all know, we can make ice. But what do? We take liquid and we do what with the variables. We cool it down significantly to freeze it, right? Well, I can actually, if under the right conditions, I can actually make water go to ice under just high pressure. I don't have to cool it down at all. I just put it under a lot of pressure. So there's different things you can do with pressure and temperature to change the state of matter. This one right here, this first bit of information is just regarding temperature changes. Because what does delta H stand for again? Heat, and there's a term for that. Enthalpy, right. And so that's a measure of heat. And so we're really looking at how heat, enthalpy, and temperature are all kind of related in this case. So, solid, liquid, who has the lower kinetic energy? The solid has a low kinetic energy because it's like practically just not moving. And then the liquid has a higher kinetic energy, right? So this is what we kind of did for warm-up. Do I put energy into this process or take it out to make it go from solid to liquid? Put it in, right? So I'm putting in energy, okay? And so is that endo or exo? Endo. All right, so tell me, nanosecond, tell me about the last one.
Slow.
Okay, so I'm going from high to low kinetic energy, so exothermic, right? So you said the solid over here has lower energy So this one's the low kinetic energy system, and this is the high kinetic energy system. So how do you go from high to low? You lose energy. Energy exits. It's exothermic. So you'll notice that these two processes are just exactly opposites of one another, right? Solid to liquid is melting. Liquid to solid is freezing. So let's say this was water, for example, and I'll tell you this delta H for water, this delta H for water, this is H of fusion. Do you remember this delta H of fusion from a couple days ago? We said fusion meant melting. Now you know, if I didn't mention that, fusion means melting. Okay, so and generally it's going to be meaning melting. But let's say this value is like 6 kilojoules per mole. 6 kilojoules per mole. This is a positive value, right? What would this one be? Same number there, right? Same process, opposite directions. So it'd be negative 6 kilojoules per mole. And so this one's called the H of fusion, which means melting. This would be called H of freezing, which guess what means? Freezing. Okay. So these values are important, but really what I want you to see is that this is a positive value because it's endothermic. This is a negative value because it's exothermic. Okay, opposite directions, equal numbers though. And so the whole definition of what does this enthalpy thing mean again, you can kind of see how I've written the units out and how it describes exactly what it is, but enthalpy of fusion, delta H fuzz is how I like to call it. Delta H fuzz is the amount of energy that's required to melt or freeze, or release when it freezes. The amount of energy required to melt or freeze 1 mole of that substance. So how is that phrase represented? It's represented as kilojoules per mole. Because remember, kilojoules means energy. And that's why I wrote it over there so you can kind of see it more in a picture form too. So write down what you need to, then give me a big goofy smile when you're ready. It doesn't have to be big or goofy. There's not much more past this in terms of new information, and we'll practice and we'll kind of come back. So this is going to be done for every single phase change. Can you predict what the next phase changes and their processes are going to be endo or exo? So what's the next one you think I'm going to go over? Vaporization and condensation. Vaporization, would that be endothermic or exothermic? Because it's going from low to high. So here I'm going to the next slide here. That's exactly what this is. So liquid to gas, tell me what it is. Delta H would be, so positive, right? So it's an endothermic process. Next one, exothermic. So delta H would be negative, that would be exo. So same situations as you're going from phases to phases that you just kind of have to pay attention to, like which is a higher energy state. So it's not a lot of new information right now, right? Kind of new stuff we learned 2 days ago. One cool fact is that people use the word evaporation or boiling incorrectly all the time. Okay, vaporization, it occurs at the surface of a liquid, okay? And boiling happens from the bottom, and now we're here. Yeah.
I think I wrote something down wrong. I'm confused. You know how you had the chart in like the very first slide?
Yeah.
I wrote going from left to right.
Oh.
No, like on the...
That one.
Yeah. I wrote it going from left to... Okay, so I just wrote it down. I wrote it down.
My bad. I was going to let you guys write down more in depthly, and we just kept going.
It's okay. I just messed up that one.
So this is all we're writing down. We're just looking at in more in depth right now. So it's basically what we just talked about. Everything going that way is endo, everything going that way is exo. Okay, so here, we're here, and I really just want you guys to know a couple of the terms that we're going to be using now. So this delta H vaporization, that is this one up here, delta H vap. Okay, what do you think this one's called? Delta H. Condensation. It's that one right there, right? Good try. But vaporization, evaporation, same thing. That's what the top one is evaporation. The bottom one is talking about gas to liquid, so that's condensation. Where do we normally see condensation? Like real life example. A water bottle, a cup, right? So you can see it in your windshield. You can see it in lots of places. Evaporation. The ocean. Okay, cool. You can think of some real life examples. Vaporization also can just occur like if I had my water bottle open, it would slowly evaporate over time, all the way, okay? So again, delta H of fusion, enthalpy of vaporization, same units. So it's the amount of heat, kilojoules, that's required to do the process, in this case is vaporization, per 1 mole of that substance. So we're going to be using those units more often. Thumbs up if this makes sense so far. We're doing okay. Okay. And this is very similar. So what's my next phase change? Okay, sublimation, which is going from what to what? Solid to gas. And where would you see that in real life? Dry ice, and I failed to go to Harris Teeter, and I will go to Harris Teeter, and I will bring us dry ice to play with tomorrow. Deal? Deal.
Have you done the dry ice bubbles?
Yeah. So, and we'll probably do something tomorrow. Okay, so sublimation is the first one. Sublimation is going from solid to gas, endo or exo. Okay, so you're talking to yourself, you're starting with the what? Low energy state, going to a high, so you have to put energy into it, so you're like, yep, that's definitely endothermic. I don't know if it's exo, but I got endo. Endothermic, delta H is positive, and then dep, what does that mean? Deposition. Deposition is the opposite of sublimation, and that one would be exothermic because you're going from so a high energy state to a low energy state, so that's going to be releasing energy of some form. Okay, so where would you see, I know you were telling me sublimation happens in dry ice, where would you see deposition? In real life. That's under high pressure. Freezing is the wrong term used for that. It's called deposition. Dry ice. So give me something else. You gotta think of something that goes from a vapor state to a solid state. It probably will happen pretty soon. People should be like covering their plants and stuff outside. It's getting cold out. Frost. Frost is just air, gas, and it gets so cold that at that temperature, it doesn't even go to liquid. It goes straight to solid. It hits the plant, I guess. Another one for sublimation is it makes things smell good, going from solid to gas.
Oh, those little candles.
Those little like, they throw scent at you and hit you in the face, right? So those like little cone air fresheners, you know what I'm talking about? That's sublimation. It works from chemistry. They make sure a room smells good. Yay, chemistry. All right. Thanks. Okay, so this is a phase diagram. It's a diagram with what on it? Phases, right? Okay, so you need to know how to read a phase diagram. If you need to sketch your own, because my copy is kind of a dark copy, and you have a couple minutes right now, sketch on the back if you want. That's what that black spot on the paper is. Yep, that right there. Copier and colorful images don't work out. So phase diagram. I'll actually leave it like that. You guys can see everything. And you'll notice that the middle line is fairly straight. This one got a little bit of a negative slope to it. I just want to point out some key features of it. So what do you notice the order is from left to right in terms of phases? Solid, liquid, gas. It will always be solid, liquid, gas. Do not go crazy and be like, I think I'm going to put gas over here. No. Solid, liquid, gas. And that makes sense because under low temperatures and low pressures, it's probably going to be a solid because low temperature means it's going to be low kinetic energy. Or even like really high pressures too definitely would be solids as well. And then opposite, under high temperatures, particles are getting really, really fast. And as they get really fast, they start to spread out, so that's more of a gaseous state. Who remembers from their reading guide what this point is called? Right, the critical point. This is the critical point of this lecture, guys. So the critical point is the point when the gas, the particles are so hot, right? They're flying around like crazy. Okay, they're moving really fast. They want to be a gas. But the pressure is so high. So what is the pressure doing to the gas? Squishing it back down to what form? It's a liquid form. So it's a fight between high temperature and high pressure, and they can't decide. So they just make it a liquid. It's a gas liquid. It's not. It's neither a gas nor a liquid. It's an indistinguishable form of matter. We cannot figure out if it's a gas or a liquid, so it's this mixture. So it's called the critical point. That temperature and that pressure creates this liquid. And I'll see if I can find a picture of one because I think they've isolated it. What do you think this point is called when all three states of matter meet? The triple point. So like we're not really creative with our words here. Triple point. So all three states of matter meet at that pressure and that temperature, and that's when they all exist there. They coexist together. Okay, so you can see these states of matter. What happens as I go from solid to liquid? That when I cross that line, what has happened? Melting. Sorry, I'm looking for a phase change. Right, so it's melting. And as I go from liquid to gas, vaporization. And I go backwards from liquid to solid. Freezing. And I go backwards. And I go here. Sublimation. And then backwards. Deposition. Right, so all those phases we just talked about are actually on a graph now, right? So if I say we exist at normal pressure, who knows the pressure at we live at? I heard it. Say again. 101.3 kilopascals, kPa, 101.3 kilopascals. That's also 1 atmosphere, right there. You see all my pressures and atmospheres here? It's 1 atmosphere. We live at 1 atmosphere. All right, cool. So where does our water boil? What temperature? 100 degrees Celsius. I'm going to prove it to you on a graph, though. At 1, so at normal, so we call this normal pressure. So normal is what 1 atmosphere pressure is. And the way you read the graph is you point at the 1 atmosphere pressure, you go over until you cross the point where boiling would happen. Was that here? No, you keep going. You go to here where the liquid and gas are intermingling, and then you drop it down and you go up. Yep, sure thing. 100 degrees Celsius. You read the temperature from the lower axes. So you need to know pressures on the y-axis and temperatures on the x-axis. Okay, so if I was on top of a mountain, give me an approximate pressure. If I was on top of Mount Everest. Give me an atmospheres. Point something. Okay, I'm hearing it. I want to make sure we all get how this works. How does pressure work? Here's my mountain. Here's us. Very little glasses or goggles on, doing chemistry experiments. Flask. Okay. Hair. There we go. Smile. It's really smiling. Okay. So we climb up Mount Everest. Right now, there's a lot of pressure pushing down on us, right? All that atmospheric pressure. What is that again for us? 1 atmosphere. Okay. I go to the top of Mount Everest. Yay! I made it. I'm cold because it's really cold up there. And how much pressure is pushing down? Right? Let's go 0.6 atmospheres. I know it looks like a lot less, but it's not that much less. Okay. And then I go and I dive into the ocean. Woo! Ocean. Fish. Okay. So. The air is thinner, and so there's less oxygen, and your cells are used to a specific amount of oxygen. There's less of it. Yes, you actually could die because there's a lack of oxygen, and also, so they usually have teams of people watching you to make sure you make it back down at a risk. And then under the ocean, what makes it hard to breathe? I was going to say the water, but, and the pressure. The pressure makes it really hard to breathe. No, the water. So under here, you've got a lot more pressure. So this might be like 1.2 atmospheres or something like that. And I'm making these numbers up. These could vary. But I want you to know on top of mountains, less pressure. Okay, so on your graph here, where is less pressure?
Down below the 1.
Down below here. Okay. So let's go here, and I want to say what temperature would my water boil at? So you go there. So you see I drew it all the way over to the gas and liquid interface, and then I go about there. Give me an estimate. 62 degrees Celsius. All right. So top of the mountain, you actually have to cook your food for longer because it's boiling at a lower temperature. So it's not meeting the temperature that is required to cook the food at. So they have different, have you ever seen on the package, if you're at this altitude, you should cook it for this long at this temperature? Look, you see it. Look at a cake. Yeah, they've got on baking and stuff like that. So you should look and it'll say, if you're at this altitude, you need to cook it for this long at this temperature, because you're never going to cook it at the same temperature we do, because stuff just starts happening earlier. It's just chemistry. Yeah.
There's some towns that are lower than sea level. Those have lower pressure. Those towns would have lower pressure.
They have higher pressure below us, right? So they cook foods for different lengths of time and different temperatures too. So their water would start boiling at like 105 or something like that versus 100. So yeah, chemistry. Yeah, okay. So let's look at. You guys have a worksheet now. Let's take a break from me, and you guys talk about this with your partner. Work on it. I'm going to give you less than 10 minutes. It is a quick deal. It says section 3, and there's 2 graphs there that are phase diagrams. Okay, you're working on the right-hand side of your page, right on this paper. The right-hand side. So take a couple minutes to make sure you know what we are talking about. I'm looking, I see most gas foldables. Oh, some of us didn't finish yesterday. Bring your gas foldables up. Some of you guys are ahead of mine. One and 3 are the same. Free question, unless you don't know it at all. 1 and 3 are the same. Right here.
Oh yeah.
1 atm. And that's our pressure, so that's what when it says normal, when we're normal freezing point, that's what it is.
Solid to
It'll be like, it's a solid. It's like,
solids can freeze.
dang, solids are frozen. Solids are frozen.
Yeah.
No, but actually, I was going to think of an ionic solid. But ionic solids, they freeze at like 600 degrees Celsius. They freeze.
What is this? Sugars. They're not solid, like. Solid though.
Raise your hand if you need me. There's somebody next to you that's incredibly knowledgeable too.
I put paper in boiling sulfur. Then yeah. Yeah. I don't know what you're working. You can like choose that. That's what I'm saying. Like you said, Joe Enlow, like a heathen. I'm saying Miss Enlow. You're using that word wrong. No, that's what it is. I know what it means. You're a bad person. Oh, isn't that it's liquid. It's like for the very first one, it's like
Alright, take like 1 or 2 more minutes on this and I'm gonna check over some of Yeah, like happy coffee.
because it always
I got this one. But then like okay, so
because that's like above 100. The critical point. So what temperature would be 100?
Alright guys, and answer takes you back in 5, 4, 3, 2, 1. Perfect. Okay. Where is normal for us? Normal in pressure. 1 atmosphere, right? So anytime you hear normal, 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 it's asking for the points like, okay, the temperatures at which these things freeze or boil, but normal means 1 atmosphere. So you probably first thing drew a line across, and oops, that's really bad, but that's not what you did. Where was the freezing point? Between what two phases? Right. So after you kind of did SLG, you said between liquid and solid, that's about there, so that was about 100 degrees Celsius, right? What was the next one? Boiling, so that's between, okay, and so you dropped it and you were like, yeah, someplace between 300 and 400 probably, because it's a little bit difficult to see on where you drew your lines. And then number 4, if I had a quantity of substance at 1.25 atmospheres and a temperature of 300, what phase of matter is that? Okay, so 1.25 atmospheres and 300 is in the liquid region. And then at the 0.25, at the same temperature, is in the wet region. Right, because 0.25 is way down here, so you'd be way down here. So you're going from liquid to gas, and then you have to identify what kind of phase change that was, which is vaporization or evaporation, right? And then where is the indistinguishable point? This dot here, right? So that's 800 degrees Celsius, which is the critical point. Okay, and then on the last couple, Oh, it doesn't go away. Okay. What? No, I have to like click these things. That's alright. These other things will just be in the way. Okay. What is the? No, that's not what I was just gonna ask. Above what temperature is it possible? Nope. There's one on here. Is there anything on here I need to go over?
I think that question was us.
Number 8. At a constant temperature, what would you do to cause this substance to change from the liquid phase to the solid phase? So if I was at any constant temperature, I only have two variables to mess with, right? Temperature and pressure. So if temperature is staying constant, the only other variable I have access to is the pressure. So what would I do to pressure to make it go from gas to
You increase the pressure.
right? So if I'm going from gas to solid, so I'm in the B section, going to A section. If I'm at this temperature, let's say, keeping at that temperature, I need to go increasing the pressure to make it go to A, to solid. Or liquid, sorry, liquid, same story. Liquid going to solid would still increase the pressure. Okay, so let's talk about, what's the other graph you see on your paper? What's it look like? Looks like stairs, right? Okay, I know I tell you most of the time chemistry is very logical and how it explains things, but this one, hold on, let me get to it. This one is called a heat curve. Heat curve, okay? So, if you need to sketch your own, I have a good little image for you here. The particles, nope, that somebody broke something. Nope. Look, that's what's happening. Ooh, wow, okay. If you would like to sketch out something, the couple terms that you should include are, not this MC delta T thing, not yet, we're going to go to that next unit. Delta H fuzz, what's fuzz mean? Fusion, which means to melt. And then H cap, vaporize, right? And what does the delta H mean? Enthalpy or measure of heat, right? So this line is smaller than this line. Why? It could be due to time differences. It also could be due to heat differences, right? So what if I told you this is due to heat differences? Explain to me why. Tell me what does it mean first. If you see a smaller line here and a longer line here. Okay, so you can apply, you apply less heat here to cause the phase change, and you apply more heat here to cause the phase change, right? Why does that make sense? Because of the molecules, right? Look at this one. They're really close together. You gotta apply like that much heat to make them separate that much. They're overcoming interactions with each other. And what do they call those interactions that are between molecules? Intermolecular forces. Do you remember this? No?
I was just saying
So when particles are close together versus farther apart, okay, those are my solid liquid gas representations. This has a little bit of heat that's needed to cause that phase change, right? This one requires a lot of heat to cause this phase change. Why? Nope, I'm not dealing with pressure at all on this one. I'm thinking you're meaning like how close they are, like how concentrated the stuff is, how close they are together. I think that's kind of what you're saying, right? So you're going with they're close together, they're not that much farther apart than these were, right? So this one's a small amount of IMFs that you're breaking, you're overcoming. So it doesn't take very much heat to do that. But if you're going from like liquid state to crazy gaseous state, you're totally wiping out all IMFs. There's no attractions again at all. They're really far apart from each other. So this one's got a lot of energy because most IMFs are overcome. And that's just kind of the phrase we use to say they're broken. So that's something you need to recognize. This over here is melting, so that's delta H what? Fuzz, right? And this is delta H vaporization. So if this one was like, and I'm going to use the example of water. Water has like a 6.0 kilojoule per mole. value for delta H fuzz, so give me something that might be relevant for this one. Huh? Yeah, so if I'm telling you the value of this one is 600 or 60 kilojoules, and I told you this one's more, 60 kilojoules, right? Something bigger. You'll be able to see it quantitatively and qualitatively based off these pictures. Okay, so let's go back here. This is the way things happen, and you guys have notes on this. Oops. You guys have notes on this here. So let's just talk about what they are, and then we'll answer a couple questions. What do you notice about the graph axes now? Okay, and what's on the side? Temperature. So you should realize that temperature on the side is meaning it's a heat curve, okay? So my other example that I have for you had time on the bottom, the other one had heat applied. So these are the two different axes that it could be. It could be heat applied or it could be time. So what do you notice that even though I'm adding heat, what is not happening right here?
No reaction.
It's not moving.
What's not moving?
The temperature.
Right, a flat plateau means the temperature is not changing. How does adding heat, most of the time adding heat means you're adding temperature, right? You're increasing the temperature.
Yeah.
Adding heat, though, does not add or change temperature in this case. So what is happening right here? What phase change is happening here? You're between phases, but what's the phase change? Melting. Okay, so what you're telling me is that phase changes, during a phase change, there is no temperature. Why? Where is this heat going? It's not a reaction either. It's just a phase change. It's making things move away from each other, right? You're just giving them energy to make them move. And when they move, they overcome their IMFs. That's why they're able to move apart and become liquid versus solid. So that's one important piece that I'm going to write out in just a second, because that's one of the hardest parts to realize. So I'm adding heat. Temperature's going up. Temperature's going up. Temperature's going up. All of a sudden, what starts to happen? It starts to melt. And as it starts to melt, so I've gone here, it starts to melt. And as I melt, the temperature's not going up, but the energy that's being applied is allowing the particles to start to move away from each other. Okay, and then it gets to the point where it's all melted, so it's all liquid. And then the liquid starts to go up in temperature, and the liquid's going up in temperature and up in temperature and up in temperature, and then it's to the point where it's going to start to vaporize, right? So go away to gas, meaning it's going to vaporize. But what's happening here? But the temperature's staying the same because where's this energy that's being added to it? Where's it going into?
It's going to making it expand.
Making them move apart from each other, right? Making them expand. And so it's vaporizing, and then it's vapor fully. Okay, so that's what these couple of questions are regarding. Which segments of the graph represent phase changes? A to B and C to D, right? That's on the graph here. A, B, C, D, those are the plateaus. And then what's happening to the temperature while the substance is phase changing? What's happening to the temperature when the particles are phase changing? Right, so there's no change in temperature. And then that's the last part is I want you to write down for yourself is what's happening to, or why is the temperature not changing? And right, to force them to expand or move apart, right? So overcome IMFs is kind of more specifically what it is, but you guys got the deal. So energy applied is used to overcome IMFs, aka move particles apart. So that's an explanation that I will ask of you on your problem set 13 sum, and then also on this test. So that's just one of the harder ones to know. But that's heat curve for you, right? So the heat curve goes solid change, liquid change, gas change. What does a cool curve look like? So downstairs, gas to liquid to solid. Okay, I want you to start on the one on the worksheet, that's section 2, and then go back up to section 1. So section 1 requires you to draw them. I want you to have a little bit more experience looking at them before you start to draw them. Work with somebody on that. You guys got 10 minutes. So it looks like this. This animated one?
Days change. I heard it's
What are we at?
3 days change.
The general term for points D is to B? No, melting. So it's more specific than phase change, but you're right on phase change, it's melting.
But then it says from D to E as well.
Okay, so, oh, okay, you would say phase change for general, but from D to C would be melting and D to E would be excitation. Oh, no, I see what you're saying. Sorry, 3 is just, is phase change, and 4 and 5 are more specific.
I don't know which side you're on, but you're all going. So I'll call for them. And low is very supporting.
I'm just trying to think
That's like a real life situation, or a lab. Oh. Well, what happened? What's like it. At least.
At least.
At least.
Okay, well, at least it was an S. Well, yeah, it was S.
All right. All right, guys. I see most of you are with part 2. Look at number 2 on number 2. I mean on number 1. Section 1, number 2. Okay. Section 1, number 2. Section 1, number 2. So I know you've not drawn them because I've not seen you draw them. So number 1 you guys can do on your own. Number 2, graph of temperature versus time. So what do the axes look like? Okay, so temp here, time here. Temp. And it says from nitrogen going from gas to liquid. So draw it in the air, kind of how it looks. Gas to liquid. Start high, slant, and then phase change, and then liquid. And it doesn't say go any further. This is a two phase one, not a 3-phase one. So you're starting here, flattening out, going here. So just put low G, put low L. All right. Nitrogen condenses at -210 degrees Celsius. Where would that go? So I'm just going to label this for us to be clear. Where would that condensation be? A, B, C, or D? B is where the first point starts to condensate. So we have condensation here at -210 degrees Celsius. At this point right here, sorry, it's difficult to see right there. And then make sure you label your axes and phase changes. What would be here from B to C? What phase change? Condensation, right? And then everything else is labeled. Yeah. All right, so you can do the rest of this. You got 5 minutes left. You probably knock them all out, man. Huh? Yeah, so if you don't finish, here's homework. Finish the worksheet. You still have 5 minutes. Do not pack up. Problem set 13, I want you to start it because you need to finish it by Monday. But I don't want you to wait until the weekend. I know you will. I'm looking for 50% of it done tomorrow. We're going to see it. And then RG14 is we're starting gases, and I want you guys have to know some gas stuff before we start. Get as much as you possibly can get done. Specifically reading RG14. That's more.
That's a clothing ship.
You remember this?
She's like, oh no, I still love it.
Well, our second year is
My grandparents are like dying, they both have cancer, like I haven't seen them in 20 years. Like, she's like, she is, but I felt so bad because they like said a lie. And like the one time, like she was like sick one time, she had been sick, and like even my manager was like, because like I called her, she was like dying on the phone, I was like, from coughing. And it was a really good lie for me. I know. She was so scared to try to like, she's like little, maybe an adorable, just like suburban kind of. So it's like, it's cute and adorable, but if you get it, like, one thing on it, like, it will attack you, like. I'm just chilling. It's like dining room the day before, and I walk into work and I'm like, the West, and then I'm just sitting there, wiping down my little tear, like looking at my reflection in the mirror, and all I hear is eat, non-stop. And I'm just like, I'm gonna yell at myself again. how? Stop making those pretend to move. And I puked all over the window for the layout on the
I was gonna smell and walk away and take
the floor. I know. And then,
I'm super tired.
no, and then I was just like,
It's actually before class. I got this gift.
because we're not supposed to use the mom and stuff.
Okay, all background on my car.
Yeah. But I like kind of like read
Outdoors annual trick or treat event will be held today from 5 to 7 p.m. in the teachers' parking lot, hosted by FFA and Junior A. Tell your siblings and neighbors to come in their costumes to collect candy. Detention will be in the cafeteria today. Thank you.
Right. Yes, pack up, pack up.
I know.